Today we're going to cover 3.9 graphing polynomial functions. Today we will be given a graph of a polynomial function and be able to identify all of our key characteristics that we have learned over the course of Unit 3. So more specifically, we will look for possible rational zeros, all zeros, real or complex, y-intercepts, and behavior, domain, and range. We'll be able to approximate where our graph is increasing or decreasing, maximum or minimum values, and be able to graph our function. Looking at example 1, based on the graph, identify whether it is odd or an even degree. So thinking back to the chart that we had, we looked at odd and even degrees, and we looked at our leading coefficients, whether they were positive or negative. When we fill in our chart, a positive odd degree was down to the left, up to the right. A negative odd degree was up to the left, down to the right. Positive even was up, up. Negative even was down, down. So remembering our chart, we are going down to the left, up to the right. So we know that our degree is odd and our leading coefficient is positive. We know that our zeros are at 0, 3, and 4. They all cut through our x-axis, so they have an odd multiplicity. Our y-intercept, we can see, is at the ordered pair 0, 0. That's where it crosses our y-axis. Our end behavior, this is where we write as x approaches negative infinity, what is our y doing? It's also approaching negative infinity in this case. As x approaches positive infinity, our y is also approaching positive infinity. The domain, so if we're looking at where is the smallest value that our graph is going to touch, we can see it goes on to negative infinity and positive infinity, so it is all real numbers. In interval notation, we notate that by negative infinity to positive using parentheses. We also can see that our range goes from negative infinity to positive infinity. When we talk about local maximums or minimums, remember a maximum is the highest an arc goes, and a minimum is the lowest something goes. So a local maximum or minimum is just looking at how high is your arch or arches, what is the tallest arch you have in your graph, or what is the lowest dip that you may have in our graph. So you want to just estimate this. So we would say our local maximum is about 4. Our local minimum is about negative 1/2. Our intervals where our graph is increasing. So our graph is increasing. We read a graph from left to right, from negative infinity to about 1. When we're talking about increasing and decreasing, you're always looking at your x-axis. So we would say about 1. So we write that in interval notation, negative infinity to 1. And then it's also increasing from about 3.5 to positive infinity. So we say 3.5 to positive infinity. The interval where it is decreasing, remember, read left to right, in this case is from 1 to 3.5. Example number 2, based on the graph, identify whether odd or even degree. So both of our ends are rising, so we know that this is an even degree and our leading coefficient is positive from that original chart. We can tell that our zeros are at 1 and negative 2. So we have a 0 at negative 2 and 1. So when we look at both of these, we see that they cut, so their multiplicity is going to be an odd number. It could be 1, it could be 3, 5. Our end behavior in this one, we say that as x is approaching negative infinity, our y is approaching positive infinity. As x approaches positive infinity, our y is also approaching positive infinity. Our y-intercept is the ordered pair 0, -1. Our domain is all real numbers, which in interval notation we write -infinity to positive infinity. When we look at the range, we notice that our graph doesn't go any lower than approximately -4.25, -4 1/4. So we put -4.25 to positive infinity would be our range. And we also located our approximate minimum value. So our approximate minimum is -4.25 because that's the lowest our graph goes. Our graph is increasing from about -1.5, and it continues to increase to infinity. So -1.5 to infinity, and we can see reading from left to right that our graph decreases from -infinity to, again, -1.5. Example number 3 says, given that x equals 2 is a 0 of y equals -x to the third power minus x plus 10, find the other zeros. So we know we can use synthetic division to find zeros of a polynomial function. So we have -1, we're missing our squared term, so we replace that with a 0. We have -1 linear term, and our constant is 10. They told us that this is a 0, so when we use our synthetic division, 1 degree less than what we originally had should be an x squared. After we drop our first term, we multiply, and then we add. We multiply, and then we add. We multiply, we add. We get a remainder of 0, so we know that, yes, this is actually a 0 of our polynomial function. And then we can take this quadratic, we can plug it into the quadratic formula because that always works, and I'm not so great at factoring. X equals -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So we have +2 plus or minus the square root. -2 squared is 4. Negative times a negative is a positive times a negative is a -20 all over -2. I recognize that I am going to have a complex root because I have the square root of -16 all over -2. So I continue my work. Square root of -16 is 2 plus or minus 4i all over -2. These are all divisible by 2. So my roots are -1 plus or minus 2i are the remainder of my roots. These each happen one time, so our multiplicity is a single or 1, so multiplicity of 1. In order to find my y-intercept of a function, I replace my x's with 0. So my y-intercept is +10. I know I have a 0 at +2. My 2 happens one time. Looking at my leading coefficient is negative. My degree is odd, so if I had a negative odd, it was up to the left, down to the right. So I know my graph is going through 10, up to the left. It's cutting at 2, down to the right. So my end behavior as x approaches negative infinity, y approaches positive infinity. As x approaches positive infinity, y approaches negative infinity. The domain would be all real numbers. So our domain in interval notation, we write from negative infinity to positive infinity, and then we've graphed our function. Example number 4 for our polynomial asks us to identify all the possible roots. So these are our p's over our q's. So if we put the factors of 32 over the factors of 1, our possible rational roots are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, plus or minus 16, plus or minus 32. So given that 1 and 2 are zeros, identify the other zeros, we can use synthetic division. So if we use 1 in our synthetic division, 1, negative 3, 42, negative 64, positive 32. Drop your first term. 1 times 1 is 1. Negative 10. Negative 10 is 32. 32 is negative 32. Negative 32 plus 32 is 0. We can continue with our synthetic division. They told us 2 was a 0. Drop your first term, multiply, add, multiply, add, multiply, add. We now had a 4th degree. This brought it to a cubic, which then resulted in a quadratic. I recognize that this is factorable. X times x is x squared. Negative times a negative is a positive 16. Negative 4 plus negative 4 is negative 8. So when I set those equal to 0, I get x is equal to 4. So this root has a multiplicity of 2, which means it's going to bounce on our graph. Multiplicity of 1 for our other 2 roots, which means it's going to cut. So we have a root at 1, a root at 2, a root at positive 4. We know it's going to cut. Looking at our leading coefficient is how we determine the end behavior. So our leading coefficient is positive. Our degree is even. So it's going to be up to the left, up to the right. The y-intercept, when we replace all of our x's with 0, is going to be positive 32. The domain is going to be, we can state that, we know it's going to be up to our left, up to our right. We know it cuts at 1, cuts at 2, bounces at 4. So our domain of our function is from negative infinity to positive infinity. You now can complete your Day 9 worksheet.